So in this video, we'll be discussing about discrete time systems. So first of all, let's try to understand what is a system. A system converts an input to output. What's the input in this case? It's just a sequence of numbers, right? If you remember, we had converted our signal, which was a continuous time signal measured from the environment. We had made discrete samples out of it, and these numbers are x0, x1, and so on. So these numbers are here as our input. We want to transform them into a useful output, which is again a sequence of numbers. So the system can be represented in this block diagram. The input is a sequence xn, and the output is again a sequence y of n. Why do I write these curly braces? These curly braces are there to say, okay, this is a sequence. So my x of n, it belongs to R for n equal to whatever, minus infinity to minus 1, 0, 1, so on. And similarly my y of n also belongs to R, the real numbers. And these curly braces mean the sequence of numbers. So this is the representation. Y of n is a function f of x of n. Okay, let's look at some examples of systems now. One simple is simply a scaling system. What does it do? It scales the input by a scalar. So my input sequence and now my output sequence is simply a scaled version of my input sequence. I can say y of n is simply a times x of n. So let us say my a is 0.5. What does that mean? Now my y of n will be simply half of x of n. So for n equal to minus 2, x is, let's say, minus 1. So my y will be minus half. For minus 1, this is 2. So y will be 1. For 0, it should be half. For 1, it should be, okay, 0.75, something like this. This will be half of half, means 0.25. So in this way, I can draw my y of n. Okay, now what is the use of this system? So it is, for example, for amplification. This is an audio signal. You want to amplify it into to a higher volume. You can simply use an amplifier, which can be represented in this form. Okay, let's look at another example, a time delay system. You have seen it in the past, but let's look at it from this perspective now. It adds a delay. My input sequence is this. The output sequence is this. Okay, I'm assuming that x of minus 1, x of minus 2, everything is 0 in this case. So it just adds 0, 0, and because in this sequence they are not existing, so I'm taking the default value to be 0. And x of 0 is coming a little later. So this is my y of 0, right? And similarly y of 1, y of 2. This is my y of 2. Right? In this way, I'm adding a delay, and I can represent this in this form. Y of n is simply x of n minus capital N, where capital N is the delay. It is a natural number, and it's a delay, or it's an integer basically. Okay, let's look at an example for n equal to 2. When n is 2, my y of 0 will be equal to x of 0 minus 2, which means minus 2 will appear here. So in this location, minus 2 will be coming, which is, the value is minus 1 here. And then again, this is 2. So this value is arriving here. Okay, this one is going to 0. This is 1. And similarly, the 0 will be here. Right, in this way you can keep drawing. So this is my time delay system. Now, what is the use? It can be used as a memory device. If I want to make a system which is, let us say, y of n is equal to x of n plus x of n minus 1, right? So I need to store my previous value, and this time delay system can be used to save that value and process it at the next time instant. Now, can I implement it in real time? Can I make a real system which is a time delay system? The answer is yes, why not? I just need to save the numbers in a, let's say if n is equal to 2, then I need to save two values. Which means my y of n will be equal to x of n minus 2. So at the current instant, I need the value 2 instants previous to this. Okay, but can I do it for capital N less than 0? Which means, let's say y of n is equal to x of n minus, let's say n is equal to minus 2, n plus 2, which means my y of 0 is x of 2, which means I need a future value. Yes, if the sequence of x is all visible, then it is possible, but if it is in the real time, I do not have the future value, so I cannot implement such a system in real time, right? For n less than 0, it is not possible. Yes, you can estimate, you can predict the value, but you cannot tell the exact value. Okay, next point is, do I need memory? How much? Yes, I do need memory to store previous values of x. How much memory do I need? It depends on the order capital N, right? These many numbers I need to save. Okay. So this brings us to some nice properties of discrete time systems. Let us look at the first property, which is causality. What is causality? A system is causal. So if for every choice of n naught, y n naught depends only on x n, n less than equal to n naught. Why we came to this problem? Because we saw that a system cannot be implemented in real time if it depends on future values, right? I'll go back to the example here. So in the time delay system, if my capital N is less than 0, it is not possible to implement such a system in real time. So that is what the causality, a causal system is that which can be implemented in real time because it does not depend on the future values. That is the whole idea, the intuitive understanding. Why do we need to define this property of causality? Because I don't want my system to be depending on future values of xn, right? Then it is not possible to implement it in real time. So in simple words, it is a non-anticipative system, right? It only sees the past values, not the future values. Or sees, or it only needs past values to compute the output. Okay, is a time delay system causal? The answer is yes, but only for n greater than or equal to 0. Yes. Okay. Let us look at another property now, which is the memory. So a system is called memoryless if yn depends only on xn and nothing else. We saw in our time delay system, we needed a memory. So time delay system for n not equal to 0, it is not a memoryless system. I do need memory, let's say for n greater than 0. But what is a memoryless system? Where I do not need to store any past values, which means my y of n is only a function of x of n. So only this value will determine my value here. So this is only a function of x of minus 1. Right? It does not depend on any other values of x. So that is called a memoryless system. What is the use? The use is, okay, you don't need a memory, so you can do real-time processing. For example, an amplifier system, it does not need any memory. You can directly do the processing. Okay, so the references. So all this, what we discussed in this video, comes from Oppenheim chapter 2, section 2. Thank you very much.